सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Having studied the basic characteristics of discrete time signals and discrete time systems, let us today take up the question of solution of the difference equation of a linear time invariant system through the classical method of solution of such equations. So, in the classical method of solution of difference equations, let us use some shorthand notation. Let us simply write yn for y of m, so that it becomes simpler to write. Secondly, we use operator E operating on yn equals yn plus 1. Just like you use capital D derivative operator in differential equations, let us use the symbol E. E operating on yn increments the argument by 1. So, Eyn is yn plus 1. Suppose you write E squared yn, it means this is the same as yn plus 2, and so on and so forth. So, this is the shorthand notation we will employ, and let us illustrate the method of solution of the difference equation by the classical approach through an example, and I will also indicate what we would do in a general case on the side alongside. So, let us take an example. In this example, we have 6 yn plus 2 minus 5 yn plus 1 plus yn is a forcing function xn, which is 0.4 raised to the power of n. Now, in using the shorthand notation, we can write this as 6e squared minus 5e plus 1 operating on yn equals 0.4 raised to the power of n. Now, for the solution of this, we follow two different steps, just as we do in the case of differential equations. We find the complementary solution and the particular solution. So, to find the complementary solution, that means the solution of the homogeneous equation 6e squared minus 5e plus 1 times yn equals 0. For that, we form the auxiliary equations by substituting m for e. So, we form the auxiliary equation, which is 6m squared minus 5m plus 1 equals 0. The roots of the auxiliary equation are, we have two roots, m1 half, m2 1/3. These are the two roots of the auxiliary equation. Once we have this, the complementary solution yn complementary is written down as a times an arbitrary constant a times half raised to the power of n plus b times 1/3 raised to the power of n. You recall that in the differential equation case, if the auxiliary solution, auxiliary equation has roots m1 half and 1/3, we would have written a e to the power of half t plus b e to the power of 1/3 t. Instead of that, in the difference equation case, we have half to the power of n and 1/3 to the power of n. To put this in a general framework, let me also give some remarks for the general case. In the general case, we may have f of e operating on yn equals a function g operating on x. That would be a general form of this equation. Then the auxiliary equation would be fm equals 0. Now we have two cases. One, all roots are distinct. The roots of this auxiliary equation, suppose they are all distinct, say m1, m2, m3, etc. Then the complementary solution would be having the form a times m1 raised to the power of n plus b times m2 raised to the power of n plus c times m3 raised to the power of n, and so on and so forth. On the other hand, suppose we have some two roots are the same, say m1 equals m2 equals m. Then the corresponding term in y and c would be, instead of a m1n plus b m2n, you have a plus b n times, let us say, m to the power of n. If three roots are repeated, then you have a plus bn plus cn squared times the corresponding repeated root times m to the power of n. That is how it goes. Now let us take the particular solution. We have yn, particular solution. This equation here can be cast in the form yn equals 1 over 6e squared minus 5e plus 1 operating on 0.4n. So when xn is of the form alpha raised to the power of n, and you have a function of e operating on that, all you have to do is substitute alpha for e. So this becomes 1 over 6 times 0.4 squared minus 5 times 0.4 plus 1 multiplying 0.4n. No longer an operator, but just multiplication of 0.4n. So substituting this is 1.6. Therefore, this becomes 1.96 minus 2. That will turn out to be minus 25 times 0.4n, which would then give the total solution then for yn equals the complementary solution a times 0.5n or half n plus b times 1/3 n minus 25 times 0.4n. So this is the complete solution, and a and b are to be evaluated from so-called initial conditions. In the case of differential equations, here we say from auxiliary conditions. Which are similar to initial conditions. Usually, say y0 and y1 may be prescribed. So usually y0 and y1 are prescribed. So if you know substitute n equals 0 and n equals 1, in this equation and those values are known, you can calculate A and B. That is how it goes. It may be, it need not be 0 at n equals 0 and 1, it could be two other equivalent conditions for this purpose. Now let us put this again, some general remarks for this. We may have Fe operating on Yn equals Ge operating on Xn. So Yn, the particular part of the solution, is Ge by Fe operating on Xn. Now if Xn is of the form alpha raised to the power of n, then the particular integral solution would be G alpha by F alpha, alpha raised to the power of n, provided F alpha is not equal to 0. Provided F alpha is not equal to 0. There are different rules for different types of forcing functions. We have taken one particular example, Xn is a form of alpha n. We do not spend more time in going to the details of the solution when the forcing function is of other forms. We leave it at that because this is all that we need to consider as far as our particular emphasis is concerned. We will emphasize more on the solution of the differential equations to the Z transform approach. This is just to give you an idea of the classical approach, so we will not pursue this further. However, one thing you would like to see is if Xn is of the form alpha n, Yn particular is G alpha by F alpha times alpha n. That means the particular integral solution as far as its dependence on the independent variable n is concerned is of the same form as Xn. That means if Xn is Z to the power of n, then Yn, the particular integral solution, is equal to Gz over Fz times Z to the power of n. So that means both of them have essentially the same dependence on n. So this is a characteristic signal of discrete time system, which we already mentioned. This is a characteristic signal of the discrete time system, something which we have already talked about. A second point which I would like to mention in passing is this is the complementary form of the solution. So if the complementary form of the solution, that is force free form of the solution, is to die out with time, this m1 and m2, whatever roots are there for the auxiliary equation, must have magnitude less than 1, because as n goes to infinity, this must decay down to 0. That means the roots of the auxiliary equation must be having a magnitude less than 1 if the complementary solution is to die out with time. So for stability, we can say for stability, the roots of auxiliary equation, that is Fm equals 0, must have magnitude less than 1. So that as n goes to infinity, that solution must decay down to 0. This is an important thing. This corresponds to the real part of the roots being less than 0 in the case of a continuous time system. Here the magnitude of the roots must be less than 1. So with this background, let me quickly work out an example of the application of the classical technique for solution of differential equations to a particular problem. Let us consider this network, which is in the form of a ladder network, where all resistances are equal to R, all are identical resistors, and you have a source here of E volts driving this ladder network. We are interested in finding out the voltage at the nth node as a function of n. So let us number the nodes starting from right 0, 1, 2, 3, etc. up to capital N. Now we can form the differential equation which governs the operation of the node voltages by taking a general node n and writing down the node equation at this. So Vn times conductance of this G plus G plus G, 3 times G times Vn minus G times Vn plus 1 minus G times Vn minus 1 must be 0 because at this node there is no source. So we have 3G times Vn minus G times Vn minus 1 minus G times Vn plus 1 equals 0, where G is the conductance, which is the reciprocal of R. So we now have the difference equation pertaining to this will be 3Vn minus Vn minus 1 minus Vn plus 1 equals 0. This can be recast in the form by, if you multiply by minus 1 and increment n by 1, we can write this as Vn plus 2 minus 3Vn plus 1 plus Vn minus 1 equals 0. So this is the complete homogeneous equation. There is no forcing function, and this is the difference equation. Now note that the independent variable n here is not is not indicating time here, but the independent variable here is the position of the node in the ladder network. So this is in contrast to the discrete time system, where n indicates an instant of time, but here it indicates the index of the node. So this is the difference equation. The auxiliary equation will be E squared corresponding to E squared minus 3e plus 1 operating on Vn. We can write this further if you wish as Vn plus, I am sorry, this is V3Vn plus 2 Vn plus 1, this is Vn only, I am sorry, this is Vn. So the auxiliary equation corresponding to that will be m squared minus 3m plus 1 equals 0. M squared minus 3m plus 1 equals 0. The roots are these. M1 equals, let us say, alpha, which I will write this as 3 plus root 5 upon 2, and M2, which will be turn out to be 1 over alpha, which is 3 minus root 5 upon 2. So these are the two roots of the auxiliary equation. Therefore the complementary solution for that will turn out to be, and that is all the solution, because there is no particular solution, because there is no forcing function. This will turn out to be A alpha n plus B alpha minus n, because the two roots are reciprocals of each other. So this is the general form of the solution of the equation here, but the y here turns out to be the node voltage, therefore I will write this as Vn. So Vn is A to the power of alpha n plus B to the power of B times alpha to the power of minus n is the general solution. Now we have to evaluate A and B knowing the conditions in the network, the boundary conditions, the auxiliary conditions. We note first V0 is 1/2 of V1. If this voltage V1 is there, that is final at the end. V0 is 1/2 of V1, because potential divider action across two resistors will tell you that V0 equals 1/2 of V1. So using that, we can show that B equals A upon alpha. You can substitute this in this equation and can show that B equals A upon alpha. So as a consequence, Vn turns out to be A times alpha n plus alpha minus n minus 1. So we have already evaluated one arbitrary constant A. The second boundary condition is obtained by noting that V capital N equals E. So V capital N equals E. And using that, you can calculate A as E upon alpha n, alpha capital N, plus alpha of minus n plus 1. So that is the value of A. So substituting this in this expression, finally you end up with the result Vn equals E times alpha n plus alpha minus of n plus 1 divided by alpha capital N plus alpha. That is the final answer for this. So you observe that we use the differential equation, form the auxiliary equation, find out the roots corresponding to that, and form the general solution in terms of arbitrary constants. We use the initial conditions, counterpart of initial conditions, we may call them boundary conditions here at 0 and n, and we found out A and B, and this is the final solution. In the last lecture I mentioned that a second method of solution of the differential equations is the iterative method or step by step method using a recursive algorithm. Now let me illustrate this by taking an example. Suppose we have differential equation for yn in the form yn equals xn plus alpha yn minus 1. This is a recursive relation which enables us to calculate yn step by step from the knowledge of the present input and the immediate past output yn minus 1. So let us take as an example case A, where we are given that the forcing function is a unit step delta n, and since we want to solve a differential equation of first order, we need to know one auxiliary condition. Let us also say that y minus 1 is 0. These are the conditions that are given to us. So using this information, we know y minus 1, we can calculate y0. So y0, substituting n equals 0 here, y0 is x0 plus alpha times y minus 1. x0 equals 1 because this is a unit impulse function. Unit impulse function has a value 1 at n equals 0. Alpha y minus 1 is 0, therefore this is 1 plus 0, which is equal to 1. Now we know y0, so we can calculate y1. y1 again is, according to substitute n equals 1, x1 plus alpha y0. So x1 plus alpha times y0. x1, because xn is a unit impulse, x1 is 0, and y0 happens to be equal to 1, which we just now calculated. Therefore this is 0 plus 1, that is also equal to, alpha times 1. This is alpha times y0, therefore this is equal to alpha, therefore this turns out to be alpha. y2, substitute n equals 2 here, x2 plus alpha times y1. x2 again once again is 0 because that xn is a impulse function, alpha times y1, which is alpha times alpha squared, so this is equal to alpha squared. So you can now see, you can continue this, you can get yn, you can easily see that yn equals alpha n. So the general solution for this is yn equals alpha n. So this iterative procedure will enable you to calculate the values step by step. Actually, once you get a sequence of values for y, you may or may not be able to find out a general closed form expression for y of n. In this case, it turns out that is alpha n. It may or may not be so. But this is a numerical procedure suitable for computer implementation because step by step you can proceed. You may or may not be able to find a nice closed form expression for y of n. In this case, it is possible for us to do so, but it may not be in general possible. It is a straightforward procedure. It has its value in that it is straightforward, amenable to computer implementation, and gives numerical results, but a closed form expression is not always guaranteed. Case B, let us illustrate this further. Now let us take xn to be un, a unit step, and once again let us take y minus 1 equals 0. So proceeding as before, y0, that is in this y0 is x0 plus alpha times y of minus 1. x0 is 1 because xn is un 1, this is 0, therefore this is 1. y1 equals x1 plus alpha times y0. x1 happens to be 1 because this un, this once continues to be 1. alpha times y0 is equal to 1, therefore it will be 1 plus alpha. y2 x2 plus alpha times y1. So x2 is 1 plus alpha times this quantity, so 1 plus alpha plus alpha. So you can now see the trend, you can immediately deduce that yn equals 1 plus alpha squared up to alpha n, which indeed is 1 minus alpha n plus 1 by 1 minus alpha. That is the general expression for yn. So if alpha quantity happens to be magnitude less than 1, then limit as n goes to infinity of yn for large n will turn out to be 1 over 1 plus alpha, because alpha raised to the power of n plus 1 tends to be 0. So the solution for that would be, it starts with 1, so it will asymptotically reach a value which corresponds to 1 over 1 minus alpha. That is 0, 1, 2, etc. See, in this difference equation, yn minus alpha yn minus 1. So that means the roots of the auxiliary equation, the root of the auxiliary equation, there is only one root because the first order equation is equal to alpha. So for stability, alpha has got to be less than 1, so it builds up like this. If alpha happens to be magnitude is greater than 1, it may turn out that this becomes very large, it may increase like this. Okay, let us take case C, where we take the input to be a sinusoid, sin n omega un, and once again let us assume that y1 y minus 1 is 0. So in order to find out the solution for that, let me take xn to be e to the power of jn omega minus e to the power of minus jn omega by 2j. So I will consider this as y1n, sorry, x1n minus x2n divided by 2j. So you can find out the solution for x1n, find out the solution for x2n, then I can find out the solution for xn. So let me say I would find the response due to e to the power of jn omega, that is due to x1n, and I will call that response y1n. So y10 equals x0, x10 in this case, plus alpha times y1 minus 1, which is taken to be 0, which we assumed was a 0. Therefore, this turns out to be x10, which happens to be 1, e to the power of jn omega 1. Then y1 1 is e to the power of j omega, because that is x1 when e to the power of j n omega when n equals 1 is e to the power of j omega, plus alpha times the old value, which is 1, this is alpha. y12 is e to the power of j2 omega plus alpha times this, alpha e to the power of j omega plus alpha squared. Like this we can go on, and you can show that in a y1n in a general case is e to the power of j omega n or nj omega times 1 plus alpha e to the power of minus j omega plus alpha squared e to the power of minus j2 omega, and so on up to alpha n e to the power of minus j n omega. This can be shown to be the general expression for y1n, and I can show this further to be equal to e to the power of j n omega minus alpha n plus 1 e to the power of minus j omega divided by 1 minus alpha e to the power of minus j omega. Now, it is a little messy, but the procedure is straightforward. Now, suppose I say if 1 over 1 minus alpha e to the power of minus j omega, this is independent of n, of course. So, suppose I call this m omega magnitude e to the power of j theta omega. So, the angle and the magnitudes are functions of omega. Then y1 of n, this whole thing can be recast in the form, you can put this in this form, you can pull up the details. It can be shown to be m omega multiplied by e to the power of j n omega plus theta omega minus alpha n plus 1 e to the power of minus j omega minus theta. That is how it will be y1 of n. Now, the response, this is the response to e to the power of j n omega. If you calculate y2 of n, which is the response due to e to the power of minus j n omega, which is this other term, this will be the complex conjugate of this, because e to the power of minus j n omega is the conjugate of e to the power of j n omega. So, this turns out to be m omega e to the power of minus j n omega plus theta omega minus alpha n plus 1 e to the power of j omega minus theta omega. Now, since the sum of these divided by 2j must be the total solution, because the input is the sum of these two functions, the difference of these two functions by 2j. Therefore, we also have yn equals y1n minus y2n divided by 2j, and this can be shown to be equal to m omega sin n omega plus theta omega plus alpha raised to the power of n minus 1, n plus 1 rather, n plus 1 sin omega minus theta. So, that is the final solution due to this sinusoidal forcing function. You observe here that this is a factor which does not decay with time. You are driving this with a sinusoidal function sin n omega, and the output also is a sinusoidal function sin n omega modified in magnitude by m omega by phase theta omega. So, this is the forced response or steady state response. Steady state response. Whereas, this portion is a transient response or which comes from the complementary solution. And when n becomes very large, alpha, if it is a magnitude less than 1, this decays with time. So, you have the forced response and transient response coming together. As far the, that is m omega times this is the transient response, and m omega times this is the forced response. So, you have m omega e to the power of j theta omega is the frequency response function. So, it depends on omega. So, if you are driving this with a sinusoidal function, the output has also a sinusoid modified in magnitude by m omega by phase theta omega. So, this is the frequency response function, which is a function of omega. You observe that when you are driving this sinusoid, to find out the final solution is a little bit complicated, a little messy, but the procedure is straightforward. Only thing is you have to involve yourself with a lot of complex algebra. And in this case, in all these three cases that we have considered, we have taken that even though we are using step by step iterative procedure, we are able to find out closed form expressions for y of n. This may or may not be easy in most of the cases. You recall that in the continuous time situation, if we knew the impulse response of a linear time invariant system, LTI system, then we can find out the response to any input to the convolution integral. We have a similar result in the discrete time case also. So let us take this discrete time LTI system, a discrete time system, linear time invariant discrete time system, and let the input be an impulse delta n, and let us say the output is Hn, which is called the impulse response. So the input is just a single sample at n equals 0, and you get an impulse response maybe like this. Now we can represent this delta n gives rise to Hn. For a general input xn, the response would be, just as in the case of continuous system, the convolution of xn and Hn. What is meant by the convolution of Hn and xn is in this case, in this continuous case, it is a integral. Here it is a summation of xn minus r hr summed on r, or alternately you can write this as xr hn minus r summed on r. Now what about the limits of this integral? Limits of the integral in general should be from minus infinity to plus infinity, but for a causal system and with a causal input, we take this 0 to n. We take this to 0 because for a causal input. XR, if the input is 0 for negative values of the argument, then there is no point in having this summation extending for negative values of r, so we take this to be 0. If the system is a causal system, impulse is applied at n equals 0, Hn is 0 for negative values of time. Therefore, Hn is 0 for n less than 0 for a causal system. Consequently, when r gets beyond n, Hn minus r becomes 0 because the argument turns out to be negative. Therefore, we stop the summation up to n for a causal system. After all, the summation here also is the same. It is the n minus and r exchange their roles. Therefore, here also r from 0 to n. So that is the meaning of the convolution. In the case of a discrete time system, the convolution is a summation. This is called the convolution summation. And as a matter of fact, it is simpler than the continuous time case, where there is an integration. Here it is a merely a summation. Therefore, this is really simpler. Now what is the justification for this result? We can justify it in this fashion. First of all, we can say that any xn can be written as, after all, xn is a sample of values, a sequence of values like this. So if you take one particular sample standing at place r, I can write this as xr delta n minus r. So xr times delta n minus r is just this sample. The value is xr and it is standing at n equals r. So just this one sample of this sequence of samples in x of n can be written as xr times delta n minus r. And you want a whole set of samples xn, you have to sum up all such values from r0 onwards for whatever you are having. So summed on r, xr times delta n minus r summed on r is the sequence of samples xn. So if you want to set the whole lot of the samples, you have to take the r from 0 to infinity. If you want to stop at a particular value, take from r equal to 0 and stop at that instant. So any input xn can be thought of as a sequence of a number of impulses standing at different values of n, 0, 1, 2, 3 and so forth, and having magnitudes x0, x1, x2 and so forth. So any input can be expressed in this fashion. Now after having said that, we can now say that delta n gives rise to an output Hn, that is the impulse response. But if you shift the delta by r sampling instance, instead of the impulse standing at n equals 0, suppose it is delayed by r sampling instance, the corresponding output will also be delayed by the same number of sampling instance. This is true by virtue of stationarity, by virtue of the fact that our system is time invariant or having constant parameters. It is a stationary system. It is not a time variable system. But instead of delta n minus r, suppose you have a constant multiplier xr times delta n minus r, naturally the response will be by linearity xr times hn minus r by virtue of homogeneity. If the input is multiplied by a constant, the output is also multiplied by the same constant. Now on the other hand, what we now have is a whole lot of these samples, not just one sample. So summation on xr delta n minus r, the whole lot will be corresponding summation of the output xr times hn minus r. This is the linearity, superposition. And that is the justification. After all, this is xn. Therefore, the corresponding result must be yn. So once you know the impulse response, you can find out the response for any arbitrary input by this convolution superposition or convolution summation. So what is it that we are really looking for here? You have, what you are doing here is we have two functions, discrete time functions, xn and hn, and their convolution summation is this. You keep one of them xn, changing the independent variable from n to r. hn minus r means you fold it, shift it, just as you have done in the case of continuous time domain. You multiply them, that also you do in the same fashion. But the product, all those products are not integrated now, but they are just summed up. That is the only difference that we have here. Let us illustrate this by means of an example. You have, let us say, hn of a particular LTA system is 2n un, and find yn for an input xn equals n un, that is a unit ramp function. So we can write this as yn equals xr h n minus r from 0 to n. Now xr is r times ur, because anyway r is going from 0 to n, ur is going to be 1 in that case, therefore this is r times hn minus r 2n minus r, and in the range of integration, range of this summation, n minus r is going to be positive because r is going from 0 to n, therefore we don't have to write un minus r, therefore r times 2n minus r, r from 0 to n. This can be further written as 2 to the power of n, because n is a constant as far as this summation is concerned, r times 2 to the power of minus r, r from 0 to n. Now how do we evaluate this summation? This summation can be, suppose you call that Sn as summation r 2 to the power of minus r, r from 0 to n. This can be written as 0 when r equals 0, 2 to the power of minus 1, 2 plus 2 times 2 to the power of minus 2 plus 3 times 2 to the power of minus 3, and so on and so forth. N minus 1 raised to the power of 2 times minus n plus 1, and finally n times 2 to the power of n minus n. That is how it goes. Now suppose I multiply this by 2sn. I multiply all these terms by 2, but I write this in this fashion. 2 times 2 to the power of minus 1, I write this here 1. 2 times 2 to the power of minus 2, that is 2 times 2 to the power of minus 1. So this goes here, this goes here, and this will be 3 times 2 to the power of minus 2, like that. That is, you multiply by this 2 but put this here. Similarly, you multiply by this by 2 and put this here. So n times 2 to the power of minus n plus 1. Now if you subtract the top row from the bottom row, 2sn minus sn, that is sn, that is, you subtract these values from this. So you get 1 plus 2 minus 1 plus subtract this from this 2 to the power of minus 2, and so on and so forth. Here you get 2 to the power of minus n plus 1, n minus 1 is of course 1, plus lastly you have n times 2 to the power of minus n. So this is a geometric progression, 1 plus 2 to the power of minus 1, 2 to the power of minus 2, right up to 2 to the power of minus n plus 1. So that can be shown to be, so Sn can now be written as 1 minus 2 to the power of minus n by 1 minus 2 to the power of minus 1. That is this quantity, minus, of course you are subtracting this from this, therefore this should be minus, rather minus n times 2 to the power of minus n. That is your Sn. And once you use that value of Sn and substitute in this, that is your Sn. Substitute over here, yn can be shown to be 2 to the power of n plus 1 minus 2 minus n for n greater than or equal to 0. That is the solution which we have obtained for this problem using the convolution property. What exactly you are doing is, you recall that HR will be like this. You can say that you are keeping one quantity XR, suppose you are keeping it constant, that is X, that will be XR, and yn minus r will be something like this, y hn minus r, I'm sorry, hn minus r. So you shift this, depending on the value of n, you shift this sequence of samples, you multiply this sample with this sample, multiply this sample with this sample, this sample with this sample, add up all those products, that will be your yn, and for different values of n you shift this. So that means as far as hn is concerned, xr, hr you shifted, you folded, shifted, multiplied, and then added. That means fold, shift, multiply, and then add, sum up. So these are the operations that are involved, which correspond to the counterpart in the continuous case, where all these are the same except in the final stage you integrate, but here you simply add them up. You can, I would suggest that you work out this problem using this graphical procedure. You establish a row of values corresponding to x of r, establish a row values corresponding to hn minus r for different values of n, 0, 1, 2, 3 and so forth. You multiply the products, add them up, and do this for different values of n. You get a sequence of values for yn which you verify will correspond to this formula, will be in accordance with this formula. I would like you to do that as an illustration of the convolution summation. So in this lecture we have started with the solution of the difference equation by the classical approach of solution of difference equations. Use complementary solution and the particular solution. We have taken one special case of how we can find out the particular integral solution when the forcing function is the form alpha raised to the power of n. Other cases we did not go into that because we did not want to involve ourselves into details of this particular technique. We also saw how the difference equation can be also be solved by the step-by-step procedure using the iterative technique. This will give us the solution in a very simple fashion. However, we may not always end up in a closed form solution, or at least the closed form solution may not be quite evident to us. We may or may not be able to find that out. And thirdly, we saw how the impulse response of a system can be used to find out the response to any arbitrary input. This involves the convolution summation, which is the counterpart of the convolution integral in the continuous time case. The technique essentially the same. You take the convolution of two time functions. Now is one time function is folded. That means the independent variable is reversed. Instead of plus r, it will be minus r. Instead of plus n, it minus n, vice versa. And then you shift it, multiply the two samples which are in the same position, and then add up all the products. That will be the convolution summation. So we see that the convolution summation works more or less the same way as in the case of continuous time situation. Or more importantly for us, we know that if you know the impulse response of any linear time invariant system, we can find out the response to any arbitrary input, both in the continuous time case and in the discrete time case, using the convolution property.